Hello everyone, my name is John BROUCEK. This is going to be my final update for this year's Material Science and Engineering O-REU program. My project this summer was to predict shape memory alloy characteristics. A little information about myself. I'm a Texas A&M aerospace engineering student from the class of 2022. I've done 2 years of research in the Material Science and Engineering department, focusing specifically on the application of shape memory alloys. So a quick explanation of what are shape memory alloys, or SMAs. Shape memory alloys are a metal that can return to a trained shape if it's subjected to increases and decreases in temperature. This process is called the shape memory effect. The temperature changes affect the microstructure of the alloy and then influence the macrostructure at values called transformation temperatures. The goal of this project is to understand at what temperature transformation occurs when we alloy different elements and compositions and perform processing on samples. The reason we want to know this is due to the numerous applications of this technology. One such example is the use of them as solid-state actuators in aerospace because they're so lightweight. They could also be used as elastocaloric cooling devices, energy harvesters, and so on and so forth. Different applications, however, require different temperatures, and if we can predict transformation temperatures, it will allow us to apply this technology to the many different applications. And to do this, we will apply machine learning and neural networks. So today, we'll begin by talking about the data set itself and the limitations of our data. Then we'll go into how we resample the data to ensure accurate training of the model. Then moving on to neural networks, how we can fit a model and interpret that data and what it outputs. After neural networks, we'll continue with the implementation of the trained model with the user interface that I created, along with the incorporation of a design of experiments into that user interface. This allows the user to indicate a range of values, and the interface will tell them the values that will provide the optimal range of results for those inputs. So a little bit about our data set. Our data set has a total of 15,186 rows of data with 187 columns. The biggest constraint of the data is that many of the columns aren't filled in. For example, one column may have only 200 data points that have reported values. And as a result, we just lack enough information to use this column as well as we might like. Because we lack lots of data from many columns, we need to do a process that will ensure we can train our neural network on enough data without artificially altering results. And we can do this through a process called resampling. To resample, we can group our data using a total of 51 constraints from the data itself. This can range from composition, processing, or testing parameters. If samples have data that lie within a similar range for all of those 51 components, they're placed in the same group. Now, if a group contains more than 3 samples, we do a process called undersampling. This is where we can randomly select 3 samples from that one oversized group. However, on the flip side, if there are fewer than 3 samples, we can use averages and standard deviation to create synthetic data points in a process called oversampling. By creating a common number of data points for each group, we now know that the model will train uniformly along the whole data set rather than targeting a few specific points that possess many similar features. Now that we have this functionality, we can train the model using a neural network. Neural networks find patterns in data and create weights for every possible combination of features. The lines that you see in the images below are representative of the weights that the model assigns to each feature as it passes through the model. By combining all of these features and the relative weights, we create something called a hidden layer, and that's indicated by those yellow dots. Then, by assigning weights to these new nodes, we can combine them to create our final output layer. So once again, combining features and weights. The difference between a simple neural network on the left and the deep learning neural network on the right is the number of hidden layers the model creates weights for. The more layers you have, the more complex the fit is. But you can also run the risk of overfitting the data and not being able to predict accurately. In addition, using a neural network also means we can't see what's happening during training. We really only see the output, not the equation that the neural network is using to fit the model and fit the data. Once we could train the data and predict our target transformation temperatures, we needed to be sure that predictions matched with the values the data set already provided. To do this, we needed to compare the predicted values of the target to the actual value that the data set provides. These 2 images depict that exact relation. We use the black line in both images to determine if the model is predicting along a 1-to-1 line. This denotes if the predicted values are matching with the actual values that the data set provided in the first place. After running the neural network, we tuned the hyperparameters, and we could see a good fit along this line, which we created after that tuning. And this allows us to incorporate this trained model with a high degree of certainty that we have a good fit. and this allows us to incorporate that neural network into our graphical interface. The utilization of the graphical user interface allows people across a broad spectrum of knowledge to be able to use the code, though they may not themselves understand it. As such, inputs we use attempt to be as universal as possible. What you can see in the images below is the inputs for the interface. You'll see on the left side the checkboxes that can be clicked to indicate a variable has been selected. Based on the constraints of graphing, we've constrained inputs to a minimum of 2 elements to a maximum of 4 total variables. So you can use any type of combination as long as you use a minimum of 2 elements with a maximum of 4 total variables. If you selected a processing variable in the 3rd column on that left-hand image, you can then go to the processing tab to insert a range for that variable. For every other value in the processing tab, you can either leave them as is at the default values, or you can change them to reflect the processing your material has already undergone. The ability to use inputs from the user allows the interface to serve the purpose of the user, which is continued in being able to select the targets of interest. The Targets tab allows the user to select the tabs you want to predict for the variables that were indicated on the Variable and Processing tabs. The left image shows all our current targets: 6 transformation temperatures, enthalpy of transformation, as well as figure of merit, or FOM, which relates thermal conductivity and density. After you complete all the inputs, you click on the Begin Analysis button and allow the model to run and output the predicted values in the form of graphs. Finally, the right image shows the Design of Experiments tab, and though this will be discussed more later, utilizing the inputs of the user allows the interface to create predictions for the target values that then need to be visualized for the user to see the influence of each variable on the predictions. Using the different combinations of elemental and processing variables, there's the possibility of 6 different graphical representations. I've included them so you could see a sense of how they appear in the interface when variables are selected. So each of these graphs would actually be put in as a separate tab into the interface. After visualizing and seeing the size of some of the regions of interest for some combinations, it became apparent additional refining of the grid for the user was necessary. Looking at the graph simply doesn't allow the user to interpret the best region to experiment on. It only supplies a range that could produce optimal values. For example, in a maximization project, we could use efficient design of experiment techniques for experimental validation of specific regions, such as the large red region on the 3-element graph on that right-hand side. We can see that that red region is very large, but we don't actually know what part of that to experiment on. So we incorporated something called Design of Experiments into this GUI or user interface. The Design of Experiments utilizes a technique called Latin Hypercube sampling. It uses a normal distribution curve aligned with the data ranges that a user provided, as shown in that picture on the top there on the left-hand side. Then, based on the number of samples you want to create, or the number of experiments you want to conduct, the distribution is divided into evenly partitioned regions, as the bottom left image indicates. Then from each region, we can select a point for each sample. We can then repeat this process for each variable of interest, as the grid on the bottom right shows. Our use of Latin Hypercube sampling in the Design of Experiments is then used with ranges of data that the user can provide into the interface. And we see an example of that on this slide. The range of data inputs is shown in the image on the left. The user can input a range of the variables of interest based on the graphical representation of the predictions supplied by the interface, as well as the number of samples that they want to experimentally create. The code then creates an Excel file using that Latin Hypercube sampling with each variable range as the limits for the experimentation. Using a Design of Experiments allows us to sample the design space efficiently to create a reduced number of samples required to better understand the region of interest for the user in the interface. While the current neural network predicts, the next step is to find a way to determine what lies in the hidden layers of the neural network by extracting the equations used between the physical characteristics. When we do this, we want to better understand the physics of the materials in the predicted model. We can do this by using something called feature engineering. This allows us to reduce the number of inputs in the data with the goal of constraining it to a total of 1 feature that we can train the model on. We can do this by combining all of the different features into 1 variable. And we can do this by using certain mathematical methods. By doing this, we can replace the neural network with a linear regression model that allows us to interpret the model that is being created and actually look at the equations, something using a neural net does not allow. Thank you for listening. If you have any questions, please feel free to leave those below in the comments. Thanks again.